Shoot, hindi na tayo naka-record. So, what we have in the diffraction, what we call gratings, this is, this is a plane or concave plate that is ruled with closely spaced group. So the grating would act like a multi-slit source when fulminated radiation strikes it. Okay, and different wavelengths are diffracted and constructively interfere at different angles. So what can we say about this diffraction grating? So we could say these are like what? Fences for light. So they have lots of closely spaced lines or slits like the tiny gaps in the fence, which are all arranged very, we could say, neatly. So when the light hits, when the light passes through or hits the refraction gratings, it's either what? Bend or spread out. And the bending of this spreading, that is what we call diffraction. Okay? So when the light passes through these tiny gaps in the grating, something happens. Okay? Instead of just going straight through, the light gets spread out into the different directions. Kind of like how when you look through the fences, you can see things differently depending on what you're looking for. Okay? So they are usually what we call useful in the variety of applications due to their ability to disperse light into its component wavelength. Okay? So if you're going to look at these diffraction gratings, they are either designed for transmission of the incident light or reflection. And modern spectrometers invariably use the so-called reflection gratings. Okay? So the spectroscopic gratings that we use, they are usually a replica of the so-called master gratings. So if you have these contemporary master gratings, they are ruled by a diamond ruling tool operated by a ruling engine. Okay? So if we're going to look at the grating that we have here from the different so if we're going to look at here at the grating, okay, so what we have here, so this is a diffraction from a blaze grating, okay, a blaze reflection grating. So what happened? Okay, so if you're going to see, the incident light makes what? A certain angle, okay, with the grating normal, while the diffracted light, so this is the incident light, the diffracted light also makes an angle that's equals to beta. So the spacing between the adjacent groups, okay, we could put it as D. So this is the grating. So see, it's just like a pen, okay? So when you have what we call the normal grating that you have there, so when the incident light, it makes an angle, okay, with this grating normal, and then the diffracted light, it has to make an angle that is beta. So the D that you have here, okay, that is the distance or the what we call adjacent groups. And the gamma that you have here, what do you call the gamma here? That's the angle, okay? Or the so-called group passage, but this one is what we call the blaze angle. And the distance L, what do you think what do you call this one? So L, that is for land. Okay. So if we're going to look at the groups, okay, if we're going to remove the groups, okay, what will happen? So this is just similar to this one, but without the groups. So let's see what happened. So this is the normal rating. So if you put it there, okay, what happened? So you have here two monochromatic rays shown undergoing diffraction at that angle beta, right? Now, if you're going to look at this, the ray 1 travels a distance further than ray 2. Okay? So this is ray 1. And this is what we call ray 2. So based on this one, the ray 1 travels a distance farther than ray 2 in reaching the grating surface and a distance farther than ray 2 on exiting the grating. Do you see that? This one travels longer compared to this one, and then they also have longer compared to what we call this one. So that is to look at the clarity when you remove the groups that you have there. So the groups that you have there is just this one. So try to imagine this as without this. Okay? So the diffraction from what we call the glaze reflection. Now, when we consider the polychromatic light, okay, striking a grating within a given order of diffraction other than the zero order, the various wavelengths are spatially dispersed because each wavelength undergoes constructive interference at different, okay, diffraction angle. Okay, so if we're going to use like a sample problem here, so for example, you consider light composed of two wavelengths. So we have what? 500 and 600 striking a grating at an incident angle of 10 degrees. If the grating has 12,000 or 1200 groups per millimeter, the D spacing is 10 to the 6 nanometer. Okay. Millimeter per millimeter. And the other one has a D equals to 12,000 groups per millimeter. That is 800 nanometer per group. So what will happen if we look at the first order? Okay. When the 600 nanometer is diffracted at a certain angle. So how are we going to determine the sine beta there? The angle, okay, of B. So we could use there M times the wavelength over D, okay, minus sine, which is equals to 1 times 600 over 833.3. Minus, what's the sign that we have here? So this is equals to incident light of 10. So what do we get? This is, I think, the only time we do some sort of a calculation. So what is B equals to here? So 1 times 600 over 833.3 minus sine 10 degrees. And then we can do it also on the other one. We have sine equals to 1 times 500 over what's the D that he has there. 12,000 group minus sine 10. So what do you get here? The first beta, 0.546. So how do we put this? Sine beta equals to 0.546. I forgot already doing the calculation for sine. So this is what we call 30-degree point 1. So what if instead of the 600, we have the 500, which has a distance, okay? Or that's not really what we call a distance, okay? So if we look at this, what we call D, that is really a value here, okay? The distance between the two adjacent groups. So what do you get? So we could say this one is 33.1. So what if it is 500 and then a distance between the group of 1200? So that is equals to what? Ano yung angle na makukuha nyo? Anyone? So ano yung nakuha nyo dun sa second calculation? 14.06? So one is the 33. Now, if you have what we call the 500, okay, for a 500 nanometer, the corresponding order, first order diffraction angle is, the book says 25.2. So I don't want to do a calculation here, okay? So that is just given the so-called, the presence of the polychromatic light. I think it's my mistake is instead of 1200, it should be 833 also. This one should be 833.3. So try to do the calculation. Yep. Because you get the 833.3 if you divide 10 to the 6, okay, with 1200 groups. So if you do that, you're going to get 25.2 uh, first order diffraction angle. Okay? Now, here, what we have is the so-called blaze grating. Okay? So, in a blaze grating that we have, so this is like a special form of grating. So if we have this blaze grating, these are usually designed to maximize the efficiency of diffraction for a particular wavelength or a narrow range of wavelength. Okay? And they achieve this blaze grating by precisely shaping the grooves on the grating surface to concentrate most of the diffracted light into a specific order, often the first or highest order. Okay? So if you're going to look at the blaze grating here as shown, in the previous slides that we have, so this is, we could say, the blaze grating. So where's the blaze angle there? The blaze angle there is this one. The one that forms the gamma. Okay? So in terms of this, what we call blaze grating, you can tilt the group facet at an angle, gamma, as seen here. So if you have it here, so that's a particular angle. So you can tilt, okay, your group there, pass it as an angle gamma, as in seen here. The zero order no longer corresponds to a specularly reflected ray. Now in B, as you could see here, your incident ray is normal to the grating surface and reflections occurs as 2 gamma. Okay? So the angle that you have here is twice to the angle that you have here. So this is your incident light and this is your specular reflection. Okay? And if you're going to look at the another thing that we have, another specialized grating, this is what the Etchel grating. So there are also specialized diffraction gratings designed to achieve high spectral dispersion over a wide wavelength range. Okay, and they usually consist of what, 2 sets of rulings, a primary grating with closely spaced groups and a secondary grating with coarser groups crossed at different angles. So if we're going to look at these what we call HL gratings, there are what we call coarse gratings, typically 100 groups per millimeter. So I don't know if you could see these 400 groups per millimeter. Okay, so the stiff side of the group is employed so as to achieve large diffraction angles. So they are typically used in very high orders. So if you're going to look here, so this is the incident light. So it passes through here, that's the what we call diffracted light. And this is the normal thing that we have. Now, most of them, if we're going to look at this one, this leads us to the so-called monochromators. And in my discussion here, I'm going to switch slides, okay, because I find the other slide that I have much useful, the one that I use in 137.1 version, 137 version that we have here. So the monochromators, they isolate what? Small wavelength band from a polychromatic source. Look at the name, mono. So the monochromators consist of a dispersive element. So it can either be what we have discussed, a prism, a grating, and an image transfer system, an entrance slit, mirrors, lenses on an exit slit. And within the monochromator is an image of a rectangular or sometimes curved entrance slit is transferred to the exit slit after dispersion of the wavelength component of the incident light. Okay? So, I'm going to make everything available in the slides once we're done with this chapter because we will end this chapter with this part here on the so-called monochromators. Start this one. Okay. Oops. And then, so for many spectroscopic methods, it is necessary or desirable to be able to continuously vary the wavelength of radiation over a broad range. So this process is what? Scanning. So usually how do you scan? Ano yung nasa x-axis when you scan? What do you have here? You have the wavelength. And then you scan. What usually the scan will come out? Right? And then you look at the one that is higher. And when you analyze again, that's where you put the monochromator, select it to a particular wavelength. So monochromators are designed for spectral scanning. There are monochromators for UV, visible, and IR radiation. They are all similar in mechanical construction in the sense that they use slits, lenses, mirrors, windows, gratings, or prisms. And the materials from which these components are fabricated depend on the wavelength region or intended use. So we can have this type of what we call prism monochromator. Okay? So if you're going to look at these different types of prism monochromators, what can we say? A prism monochromator, they are usually used for what? Disperse your light. Okay? Disperse your electromagnetic radiation, either UVBs, infrared, okay, you use prism. Now, you have two types of this, what we call prism design. You have Cornu and the Litco. Okay? So what is, we could say, the difference between this, what we call Cornu, okay, versus the Litco? So it has something to do with what? A design? Or has something to do, we could say, with how, okay, the light passes through here. So if you have the type, it has what? A 60-degree prism, which is made either from glass or quartz. And when the quartz is used, there's two 30-degree prism. One should be left-handed and the other is right-handed. They're cemented together in order to get the 60 degrees. So this is necessary since natural quartz is optically active and will rotate light either to the right or left hand. Now, cementing the left and the right-handed prisms will correct the light rotation and will transmit the beam in a straight direction. Okay? So if you're going to look at this, this is your light. So when it goes there, goes here, okay? And there's what? Refraction here, reflection on this side, and then on this, you can have this coming out, okay? And there's some sort of a reflection and refraction coming from this one. So based on this cornu prism, okay, the tendency that you have there is this different of light rotation and transmission of the light beam. Okay, so the cornu type of this what we call prism monochromator, they said it's just a graphical representation of the Fresnel integrals, which describe the behavior of light waves as they undergo diffraction or propagate through the optical system. Okay, so it's particularly useful in optics for analyzing phenomena such as diffraction patterns, wave front propagation, and optical path differences in interferometry. Okay, now the Litgro prism, so you have what? Instead of two 30-degree prism, you only have one. It uses the same phase for input and dispersed radiation. So if you put the light there, okay, most likely, okay, it can undergo reflection, okay? So the beam is reflected at phase perpendicular to the base due to the presence of a fixed mirror. And a litho prism would be used when few optical components are what we call needed. Okay? Now, if you're going to look at the monochromator, so usually this is what you will see. An entrance slit, collimating lens or mirror, a dispersion element, it can be prism or grating, a focusing lens or mirrors, and then the exit slit. Okay, so the one that they use instead of this, what we call the prism grating, we use the reflection grating. So if you're going to look at these reflection gratings, what do you have here? Usually the light hits the grating and disperse. So the tilt grating to you can tilt the grating to vary which wavelength pass at exit slit during the scan. So for instance here, the Czerny-Terney grating monochromator. Okay, so what happened in the Czerny-Terney monochromator? If you're going to look, okay, at here at this type of monochromator, so you have an incident radiation passing through the entrance slit. So there's light. Okay, so it can go that way, go here, or that way, goes here. So what happened? Okay, so the entrance slit at the focal point acts as a point source. Okay, for the mirror, the collimating mirror, which produces parallel radiation for the dispersion element, which in this case is a reflecting grating. So what does the grating do? It disperses the spectral component of the radiation, the incident light, right? And then it passes through again in what? Second mirror. So the first is the collimating mirror. What do you think the second mirror called? So if this is what we call the collimating, so the other one could be the focusing mirror. Okay? And from the focusing mirror, what do you produce? So it's going to produce, okay, rays that will go to the exit slit, the one that you have here. So by that time, in the focusing, you already narrow the light that you have for a particular wavelength. Okay? Everybody got that? How the Caesar-Turner grating monochromator works? Because if you're going to look in the Caesar-Ni grating, you have what? The entrance slit. So the monochromator begins by admitting light through this adjustable entrance slit. So this controls the amount of light entering the system and helps determine the spectral resolution. And then what you do, you have what? The columminating mirror. Okay, so after passing through the entrance slit, the light encounters columminating mirror. It can be other optics here. Okay, but usually the one that they commonly use is what? A mirror. It could be a lens. Okay, so what happened? The light encounters the columminating lens or mirror. It typically consists of a concave mirrors or set of lenses. So these optics ensure that the light rays leaving the slit are parallel to each other, resulting in the columminated light. So what happens? So the columminated light, after passing through here, it goes to the reflection grating. So this reflection grating, that is a diffraction grating. So the columminated light strikes a diffraction grating, which disperses light into its component wavelength. And the grating can be rotated to select the desired wavelength. Remember, we have a monochromator. So you're narrowing down the light that you enter in the entrance to a certain wavelength. Okay, and the diffraction angle determines which wavelength is focused at the what we call going to the exit slit. Okay, so based on the diffraction, it goes to the focusing mirror or lens. Okay, so it focuses the dispersed light into the exit slit, and this ensures that only the selected wavelength or narrow band of wavelength reaches the detector. Okay, so that's how this so-called Caesar-Turner grating monochromator works. Okay, question? I think there's a discussion of this in the, if I'm not mistaken, an undergrad thing. Now, how is it differ from the other one? How does it differ in the so-called the Bunsen prism? Okay. So the Bunsen, we could say prism monochromator, it also operates on the, we could say, principle of dispersion. So what happened in this, what we call the Bunsen burner prism? So here, you're going to have a prism that is made up of the transparent material. So what happened here, when the white light enters to the prism, it gets dispersed into the component. So we have, we could say this white light. So it passes through here, again, columminating light. So instead of, we could say, a reflection grating here, it passes through the prism. Okay? So what does the prism do? It disperses the light into component wavelengths, right? Due to the varying degrees of refractive indices of the material. So based on that, you're going to get different wavelengths. So you can see here, there's a lambda 1 and a lambda 2. So that is what we call pertain to whatever wavelength that you want. So what happened? Okay. So the dispersion that separates the light into the spectrum with different colors emerge at a different angle. So how are we going to select here the wavelength. So usually there's a slit that is placed at the exit point, and you adjust the position and the width of the slit. Okay. A specific wavelength or a narrow range of wavelengths can be selected from the dispersed spectrum. And this slit usually acts, okay, like a filter, allowing only the desired wavelengths to pass through while blocking the rest. Okay. And whenever they exit, what do they have there? Usually both of them, they have detectors. So that's why we could say the two types of these, what we call reflection gratings that we have. Now, which do you think is more common? In terms of design, which is more simple between the two? Anyone? Which do you think is more simple? Is it scissor-knee? So both of them can be used for spectral analysis. They differ in what? The design, the spectral resolution, flexibility, and cost. So which do you think is more simple? Which do you think is cheaper between the two? Anyone? You type A or B. Which is cheaper? Remember, one is really a reflection grating, while the other one is just what? A prism. So right away there, you will know which is cheaper. So which do you think is cheaper? Okay, the first the letter B is the one that's cheaper, because look, this prism is cheap compared to a reflection grating or a grating. So we could say in terms of cost, okay, and simplicity, the Bunsen prism monochromator is what we call useful. You can what we call this, made it from scratch. If you have some budget constraint, like in the Philippine setup, you can make this what we call Bunsen burner. They're more affordable and simpler. Okay, compared to this what we call scissor-knee turner. Okay. Now, how about between flexibility and adjustability? So usually, the cheaper one, they're not flexible, and you cannot adjust it. Okay, so they have limited flexibility and adjustability compared to the scissor-knee turning. Okay, so the adjustment options that you have may be limited to the slit width and prism position. In the scissor-knee turning, you can what? Adjust most of the parameter there, so it offers greater flexibility. Okay. Now, how about in terms of range of wavelength? Which do you think win in terms of what we call wavelength range? So usually the cheaper, okay, medyo mahaba or wider yung range na nakukuha niya. Okay? While the scissor-knee turning, it can cover wide range, but if you want to select a wavelength of interest, I think it's much better compared to the Bunsen prism monochromator. Okay? And then in terms of spectral resolution, I think the scissor Eternity will give you a high resolution. Kasi gratings yung ano mo eh, kaysa sa prism. Ito yung ano dyan eh, main difference eh. So paano mo i-adjust yung wavelength na gusto mo dito? I-adjust mo yung prism, but usually, ano gagawin mo? Mano-manong adjustment. At least this, you can find, okay, I want this wavelength to come out. So the grating will be the one to adjust that. So that's the difference between what we call the two. And if we're going to look at this, what we call grating monochromators, okay? So we could say this is a reflection grating, but since there's a grating there, we can also say that this is a grating monochromator. That's the one that is what we call being used, okay? So currently, nearly all monochrome are based on the reflection gratings because they are cheaper to fabricate. They provide better wavelength separation for the same size dispersing element and disperse radiation linearly along the focal plane. So when you have linear depression, it means that the position of the band along the focal plane varies linearly with its wavelength. Okay, so for prism instrument, the shorter wavelengths are dispersed to a greater degree than are the longer ones, which complicate instrument design. So the way you look at this here, so look at the shorter wavelengths that you have here. So you have the grating, okay? So if you're going to look at this 200, 300, 400, 500, 600, 700, and 800. Now, compare it with the glass prism. Ano lang nakakover ng glass? You cannot use this one because it will be absorbed by the glass. So you can only work 350 and above. Now, if it's a quartz prism, okay, you go here, okay? But if you're going to look at this, look at the difference here. Hindi siya uniform in comparison with the grating. Okay? So, what does it do is, based on this one, it will give you the distance y along the focal plane. So, at least, yung grating consistent compared to the prism. And I discussed to you about the so-called echolate gratings. Okay? So typically, the echolate gratings, they contain about 300 to 2,000 lines or grooves per millimeter. But an average line density of about 1,200 to 1,400 lines per millimeter is most common. So what they do, they use the long phase for dispersion of radiation. It is the grating of choice for molecular spectroscopic instruments. So mas okay ito, okay? Echolate compared to what we call etchel. So meron pang etchel compared to echolate. So what's the difference? One we could say is the fine one, and the other one is the coarse group. So one use the long phase for dispersion, and the other one would use the short phase. So how do you know the long and the short phase here? This is the longer one, and this is what we call the shorter one. So between the two, they prefer this one. So if you're going to look at the etchel monochromator, so this is what you have. So what does the etchel do? It goes to the short phase. So when you have the light passing through it, there's a 30-degree angle prism that you have there. So this is what the litho type. So from whenever they go there, it gives you the different wavelength. Now the prism dispersion, as you could see here, they're not what we call uniform. They are longer at shorter. wavelength. Okay, the prism dispersion is much higher at shorter wavelength, if you see here. Now, how do we look at this monochromator performance characteristics? Okay, so these are, we could say, the 5 performance characteristics that you're going to look at. And we're going to go on this, we could say, one by one. Okay, so one is this so-called spectral purity. So there's 4 main properties that can assess the performance of the grating monochromator. So one is spectral purity. So if we study thoroughly the exiting beam, it will always be observed that it is contaminated with small amounts of wavelength, far from that of the instrumental settings. And this is due to the following reason. So you have the exiting wavelength. So you want at least what? Kung ano yung pinasok mo na wavelength, yun din dapat yung lalabas. But, okay, because of some factors, it doesn't happen. You have the so-called scattered radiation and stray radiation that can affect the purity. So scattered radiation, you have dust particulates in your system. So it could cause this what we call the scattering of the light. How do you resolve this drawback? You seal the monochromator entrance and exit clip by suitable window. And this is more problematic in a third world country, right? Here, we sometimes we open, walang cover yung mga UVBs namin. Okay? Another thing that can affect the spectral purity is what? The stray radiation. So this is radiation that exits the monochromator without passing through the dispersion element. So dumidiretso na yung what we call the stray radiation. That's what is stray. And you can solve this as well as the other problem related to spurious radiation, including scattering, by introducing baffles at appropriate location inside the monochromator, as well as painting the internal walls of the monochromator by black. Why black? Why do we use black? Anyone? Bakit black? They usually what? Absorb the light across a broad range of wavelength. That's just one thing. Okay? Alin pa? Nag-absorb siya ng light. Ano pa? Nagre-reduce siya ng reflection. Okay? So, there are many, we could say, reason why what we use black. Kaya nga sabi nila, ano yung common say that? Dahil kapag summer, wag kang mag-black. O mag-wear ng black shirt, right? Kasi lalong mas mainit. Kasi ina-absorb niya lahat ng init. Okay? So aside from the scattered radiation, stray radiation, you also have the so-called imperfections. So there are always imperfections doon sa lenses or mirrors too. Broken or uneven blazes, uneven lens or mirror surfaces. So this would lead to some problems regarding the quality of the obtained wavelengths. Now the next one is dispersion. So dispersion is the ability of the monochromator to separate the different wavelengths, and the angular dispersion can be defined as the change in the angle of reflection with the wavelength. So if you're going to look at this, this is the one that we have discussed earlier. Okay. Dispersion, more or less, the reciprocal linear dispersion of the grating, it will affect a small angles like 20, less than 20-degree angles. It can cause our approximates to unity, which suggests that the reciprocal linear dispersion will be d divided by n over f. Okay. What else? So if we have this dispersion of what we call the gratings, usually refers to how effective the diffraction grating spread out the different wavelengths of light. So think of it as how much of the grating can spread out the different colors of light so you can see them separately. So if a monochromator has a high dispersion, it will spread out light, the colors of the light, so you can clearly see each one, while one with lower dispersion might not separate them at all. And then the next one is resolution, the resolving power of MC. How do you define resolution? I think, where do you find it? Chromatography, right? So resolution in chromatography is how separated how well separated the two peaks is. So in spectroscopy, it's the ability of grating monochromators to separate adjacent wavelengths with very small differences. The resolving power of the grating or resolution. So here, wavelength over the difference or change in wavelength, where change in wavelength is the difference between the two adjacent wavelengths, and wavelength is the average. So what do you want? Higher resolution, better monochromator. Okay? Because the resolution or resolving power measures the monochromator's ability to distinguish between closely spaced wavelengths of light. It's like how well the monochromator can tell the difference between two very similar colors of light. So if you have high resolving power, it can clearly separate two very close shades of color. While one with lower resolving power, they may mix them up. Okay? The next one. So how you do better resolving powers, longer gratings, higher blaze density, and higher order of diffraction. Now, the light gathering power of this, what we call monochromator. So this is the ability of your grating monochromator to collect incident light from the entrance slit. It's also important as only some of this radiation will reach the detector. And the speed, which is F divided by the numbers, a measure of the ability of the monochromator to collect the incident light. And this is what we call the speed. Okay, for most of this monochromator, they can range from 1 to 10. So light gathering, we could say, power. So it refers to how efficiently the monochromator collects and focuses light into the detector. It's like how the monochromator catches the light and directs it where it's needed. So the monochromator with the high light gathering power, they can efficiently collect and focus light into the detector, resulting in better signal strength and sensitivity, while the one that is the lower light gathering power might lose more light. And then what else? So if we're going to put at the characteristic of a conventional and actual monochromator, so look, focal length the same, group density, this is much higher, diffraction angle, so this is much higher, order, this is much higher, resolution, this is much higher, reciprocal linear dispersion, okay, this is higher, and light gathering power, so F over 98, and this is F over 88, so this is much higher. So see the difference between these two types of, we could say, monochromator. So focal length, this is what? The distance from the collimating optics to the point where the light is focused into the detector. It's like the distance from the eye of the monochromator to where it's looking at the light. So a longer focal length might have a better resolution but may require more space, while one with a shorter focal length might be more compact but might sacrifice some resolution. So the slit, so the slit can be what? Made wider or narrower. So how does it affect the thing? So a slit is machined from two pieces of metal to give sharp edges that are exactly aligned, same plane, and parallel. So since the effective bandwidth of the monochromator is dependent on its dispersion and the slit width, careful choice of the slit must be done. For burst wavelength resolution, you need a narrower slit. But the thing is, as the slit width gets narrower, the radiant power reaching the detector will decrease. So if you narrow the slit, there's only what? Less light that goes in. But at least it focused to the wavelength that you're looking for. Okay? And that could also be bad for what? Quantitative analysis. I don't know if you encounter this split. Usually in spectropolarimeter, so you have there 2.5, 5. So which is the best? Well, it depends. Because it's a compromise between detectability and resolution. Wider slit, okay, more power, but the resolution might be not good. Okay, narrower slit, higher resolution, but the power might not be enough to generate signal. So if you look at the effect of the slit width on the monochromator resolution, so this is how it happens. Okay, so this is what we call the bandwidth. So depending on what you have, okay, this is the effect of the entrance is illuminated with 3 wavelengths only. So entrance and exit waves are identical. So plots on the right show changes in emitted power of the monochromator is varied. So complete resolution of 2 features only possible when slit is adjusted to produce effective bandwidth, half or less of difference between the 2 wavelengths. So look what happened here. This is much wider, and then make it, and then this one is much narrower. And how they are what people affected. And you can look at it in terms of benzene. So look, 0.5, 1, 2. So look what happened to the resolution. You may ask, which is the best? A, B, or C? What can you say here? They're sharp, right? But not separated. Here, you cannot separate it. But what happened? So the reading that you have here is much higher. The thing is, this is sharp. Now, these are all vapors. That means benzene, vapor. It's between 220 and 275. So that's the compromise of your what we call narrow and wider, what we call split. So I end this chapter here. And next thing that we're going to talk about is, we could say, the light source. And of course, we're going to start it with the one that starts all, the black body radiation. So maybe a little bit of Gen Chem, if you recall your Gen Chem. Why black body radiation? Because that is usually one of the good source, or one of the light sources that we can have on. So the first part of our lecture was not recorded. It's so hot right now. We started the morning at 45 Fahrenheit, and then it reached 70.